you have something like sine of x over x, which definitely makes sense for x different from 0, okay? But at x equals 0, the quantity is not defined. The denominator is equal to 0, well, as well as itself. So now you want to compare two quantities which are both small, right? You take the ratio. So, and two small quantities, I mean, the ratio of two small quantities can be anything, as you know, right? Because being small is just, because what you're measuring is not the separate smallness of the numerator and the denominator, but the ratio. So I can be small, but way larger than you, okay? The size of a molecule, it's way, way larger than the size of an electron, right? So it's like, you can have two very small things, but their ratio can be very large or very small, or actually they could be comparable, right? So, and the theory of limits is exactly what you need to answer to the question, what is the size of this object at x equals 0, okay? So what is the size of this object as the two things I'm comparing become smaller and smaller, but how can I decide if the ratio is becomes closer and closer to a definite quantity or not? And that's exactly what we do. So for this reason, it's important to keep this in mind, and to keep in mind the fact that we're working with functions defined on an interval minus a point. Okay? So our setting will be, we are given an interval I, so I will be, say, an open interval AB. We pick a point inside this interval, x naught, or maybe let me call it C, as in your book, okay? And then we consider functions, f of x. So our functions will be defined on AB minus the point C. So here the function could even be defined, but for what I want to do, it's not important. Okay, even of course you can always, given a formula that doesn't make sense at the point C, you can always tell me that formally I decided my function at C takes the value 500 or 0 or what you like. But the point is that we are not interested. We are somehow interested in understanding, given the function that you define at the point C, okay, we want to understand how to describe the behavior of the function close to the point C. Okay? So you could have, for example, you could have a function that near this point C is doing some wild oscillations, okay? And so the question is really how can we describe what happens when we come closer to this point? So typical example is indeed, I don't know, whenever you try to compute a derivative, right? For example, if you want to compute the derivative of the function sine at the point 0, that's the incremental ratio of the function sine of x at x equals 0, right? That's sine of x minus sine of 0 divided by x minus 0. If you want to compute the derivative of the exponential function at 0, you will be confronted with a quantity like that, e to the x minus 1, which would be e to the x minus e to the 0, divided by x minus 0, the incremental ratio of the exponential at the point 0, right? So this would be sine of x minus sine of 0 divided by x minus 0, and this would be e to the x minus e to the 0 divided by x minus 0. These are all examples that I would like to understand. Another example, classical example you want to understand is cosine x minus 1 over x, because this is cosine of x minus cosine of 0 divided by x minus 0. So you see, the typical thing is looking at the incremental ratio of something, right? Do you see my point? Yeah, I mean, so the situation I am describing, it really comes into play when you try to compute derivatives, okay? Because when you try to compute derivatives, typically, you are comparing, when you try to compute a derivative, you have to write down the incremental ratio of your function at a point, right? And incremental ratios, you see, they always come up in this fashion. So it's something that is not defined at the point where you want to take the derivative. So somehow the abstract framework for describing these is I am given an interval, a point inside an interval, a function defined around the point, okay? And you see, in all these cases, I don't have a way of defining. This formula doesn't give me immediately a way to define this function f of x at the point 0, which is meaningful, simply because I cannot directly compute. Okay? So that's why limits are introduced. Essentially, limits are introduced to make sense of derivatives. Then, of course, they are a much more general tool. Okay? So it's not that you use limits just to understand the limit. Then you can do many other things. But really, the origin of the definition of limit is to try to make sense of what you do when you define a derivative. Okay? So even though, I mean, there is no need to introduce the concept of derivative at this level. So these are all kind of examples of what I would like to do, right? So in all these examples, I have c equals 0, and I have functions that are defined on, so ab minus c in all these examples would be the full line minus the origin, right? Because my functions would be, my f of x will be defined in all the line minus the origin, and somehow I want to understand in these cases what happens close to 0. Does it make sense so far? These should be familiar things, right? Okay. So, I have my interval, I have a point c inside my interval, and I have a function f of x defined on ad minus c. So, I give a definition. I say that L, a real number, is a limit, actually it will be unique, of f of x at the point c if for every epsilon positive f of x is epsilon close to L, for every epsilon positive, there exists delta positive, such that f of x is epsilon close to L in a delta neighborhood of C. Okay, so let me explain my terminology here. So my terminology is the following. Let me give a meaning to the various terms I have used, okay? So what does it mean for a function to be epsilon close to a number L somewhere? As you can imagine, so meaning of the various terms, right? So f of x epsilon close to L on a set S. By this I mean that f of x minus L is less than epsilon for every x in my set S. Okay? So when I say that the function is epsilon close to a value, L on a given set, I'm just telling you that the values of f are somehow between L minus epsilon and L plus epsilon. So this is equivalent, right? To say that L minus epsilon is less than f of x less than L plus epsilon for every x. So this is what it means that my function is epsilon close to a number f. Okay? Good. Then, So my condition is that, apart from this, for every epsilon there exists a delta. But if we go back to the definition, what's written here is that I want f of x to be epsilon close to L on something that I've called a delta neighborhood of C. Okay, that's a specific set. So that's the set S that I will put here. Okay, the set S that I will put here in the definition of limit is the delta neighborhood of C. So what is a delta neighborhood of C? So a delta neighborhood of the real number C is the interval, let me say the puncture interval C0 minus delta C0, C minus delta C union C plus delta. To draw a picture, this is the point C, this is the point C plus delta, this is the point C minus delta, and the delta neighborhood will be the union of these two open intervals. I'm taking away C out of my delta neighborhood definition since the function is not going to be defined on C necessarily, so I don't even want to bother taking the risk of computing F at C. Okay? So that's why I'm just taking away the top. So now let's try to put everything back together, okay? And look again at the definition of limit. So what I am asking is that for every positive value epsilon, there exists some threshold delta such that f of x is epsilon close to the limit value L on the delta neighborhood of C, which in formulas is just such that, so this is an if and an if, so what you are requiring is that L minus epsilon is less than f of x less than L plus epsilon for every point x lying in C minus delta C union C plus delta. So, if this is my point C, so here nearby there will be A and B. Here there is this candidate value L for the limit of my function. So all we are trying to do is to play this game, right? So we say for every epsilon, let me open a window around L. So, and I have, you see, kind of a slab into the plane, right? Which is all those points in the Cartesian plane was y coordinate is between L minus epsilon and L plus epsilon, okay? And then what I do, I say, well, given open a window, so this will be 2 epsilon, then I want to say, well, now find a sufficiently, so say that my function looks something like that, then my function looks something like that, using my f. Essentially what I'm doing, I say, okay, well, given that I have opened this window, now let me maybe do something more dramatic. Okay? So I just try to find some symmetric neighborhood of C, of the form C plus delta, C minus delta, such that all the values of my function in this interval lie between L minus epsilon and L plus epsilon. Okay? And all I'm saying is that I want to be able of doing that for every epsilon. So for every epsilon, you see, as usual, if I choose a smaller epsilon, if now I try to play the same thing but with epsilon as big as that, what happens? I have just to pick a smaller delta, corresponding delta, right? Because if I just take a smaller epsilon, okay, you see, in order to have the graph of f being trapped between L minus epsilon and L plus epsilon, I have to take a correspondingly way smaller delta. Okay? So, and all I am asking is that no matter how small the epsilon, I can decrease the size of delta such that my function will then be boxed between L plus epsilon and L minus epsilon above this little neighborhood delta. Okay? So that's the way you figure out what is a limit. You don't need to compute the function at C by using the formula, you don't need anything like that. You just need to be able to check what happens to the value of your function close to the point C. If they are well behaved in the sense that for a certain limit value, no matter how small the window you create around the limit value L, you can find a suitably small window around the point C, such that all the values of your function nearby are close to that value. Then you say that L, in a sense, is the limit of your function, and in a sense, is the correct value of your function at the point C. It's really the value that your function wants to take at point C. Okay? So that's the philosophy of the thing. Do you have questions so far? Yeah.
Why do we call it a limit if it's not? Are we? Because to me, intuitively, like the limit of f of x is what f of x does, like at infinity or negative infinity, not like just right in the middle of f of x.
Well, but think about the examples I just gave you, right? So take e to the x minus 1 over x. So can you compute that at 0, at x equals 0?
No.
You cannot, right? Nevertheless, even if you can compute it from this formula, you can check that this quantity is epsilon close to 1 on sufficiently small delta neighborhood of 0. So for me, this quantity at x equals 0 is 1. In the sense that the limit as x goes to 0 of this quantity, and this will be our notation, is 1. Okay? So you see, I'm doing something which is really like computing a limit at infinity or at minus infinity. I am extrapolating an information that is not inside my formula, right? So for example, when you tell me that this function at infinity converges to 1 as x goes to plus infinity, right? Just talk about limits that are more familiar to you at infinity. What are you telling me? You're not computing these at plus infinity, and it makes no sense. You are just telling me that I am epsilon close to 1 provided x is large enough. Okay, and the more I want to be close to 1 with this ratio, the larger x has to be. So it's the same philosophy. It's just that to catch a limit at infinity, you work with bigger and bigger numbers x. Somehow you're taking delta neighborhoods of infinity. The delta neighborhood of plus infinity is all those points larger than 1 over delta. The smaller delta, the larger the points, right? And here we are doing that at a finite point. And the motivation for doing that at a finite point is just essentially understanding ratios of elementary functions. Because that's essentially, that's very important for doing anything. Does that answer your question?
Yeah.
Do you have other questions on the definition? Okay, so now let's do. Okay, let's try to get more familiar with the definition by proving some properties. Okay. So we are given our interval, the point, our function defined on the interval minus the point, and we say that, so our definition is that L then is the limit as x goes to c of f of x if for every x being positive I can find an opening delta such that f of x minus L is less than epsilon for every point x belonging to c minus delta c union c plus delta. Okay? I will make an effort to write the definition of limit in a different way each time I write it down. Okay? It will be equivalent, but this should help you in realizing different ways of seeing this thing. Okay? So first of all, the limit is unique. The limit is unique if the limit exists, then it is unique. So the proof is extremely close to what we already see, right? So remember what we said about the sequence, right? If a sequence has different limits, I will be ultimately epsilon close to this one, and I will be ultimately epsilon close to L2. Which means that for every value large enough, I will always be here, and then for value large enough, I will always be there. But I can take the larger thresholds of the conditions, and this will force all the terms of the sequence to be both here and here. But these are disjoint, so this is impossible, right? And now the proof for functions is exactly the same, right? So we would say, well, let L1 and L2 be two different limits of my function f of x at C. Okay, let me open a window. So when I use functions, I like to draw L1 and L2, right, on a vertical line. So let me just open windows here, which are disjoint, right? So I will take epsilon small enough to have these windows around L2 and L1 disjoint. So let epsilon say equal to L2 minus L1 over 4. I am assuming that L2 is strictly larger than L1, as I can do without loss of generality, because if they're different, one will be larger than the other. So I just have to decide to call L2 the largest. Okay? Okay, so given these, I can find by the definition of limit, there exists some positive number delta 1 such that f of x takes values in an epsilon neighborhood of L1 for every x such that the distance from C is positive and less than delta 1. Okay, so notice that here I have cooked up another way of writing down the condition of being in the delta neighborhood, right? So I can write x is C minus delta, C, comma, union C is equals delta. I can tell you 0 strictly less than x minus C modulus strictly less than delta. They're all equivalent. Probably I will stick to this one because it's the one that allows me to write the least. But they're all the same. Okay? And at the same time, there exists a threshold delta 2 such that the values of f of x are away from L2 at most by epsilon for every x which lies at distance positive and less than delta 2 from this guy. So you see here there is the point C, and I'm saying that if I move away by delta 1, then all the values of my function happen to be in this box, okay, are epsilon close to L1. But then I'm also telling you something a bit scary. I'm telling you that there is another interval, let us call this C plus delta 2, okay? So this would be 2 delta 2. And I'm telling you that inside this interval, actually the values of my function are all trapped up here. And that's clearly possible, right? So peak delta to be the minimum of delta 1 and delta 2. This would be choosing delta to be delta 2 in my picture, okay? In the proof, I don't know if delta 1 or which is the smaller between delta 1 and delta 2. I can choose L2 to be larger than L1, but then the machinery of the definition gives me delta 1 and delta 2 and reverse. So pick the minimum of the two. Since you're taking just the minimum of two positive numbers, this will still be positive, trivially. And what happens if I pick, and if x is such that implies a distance delta from C, then I have both the inequalities. So I have L1, I have fx minus L1 less than epsilon, and at the same time I have fx minus L2 less than epsilon, and that's big trouble because this implies that f of x wants to be less than L1 plus epsilon, which by definition of epsilon is L1 plus L2 minus L1 over 4. But at the same time, it implies that f of x is larger than L2 minus epsilon, which is L2 minus L2 minus L1 over 4. Now, if we compute what these numbers are, takes a second. Let's do it. Okay. So the first one is, so it's clear that by construction it's clear that this is going to be strictly less than that, right? This guy, L1 plus epsilon, the way we construct it is going to be strictly less than L2 minus epsilon. Okay, let me do this, just to, let me, I will rewrite this in a second, just to, because I see your faces and I'm a bit worried. So up to here, we are all right? I mean, this is clear. Okay. And this will give me a contradiction which gives f of x strictly less than f of x, which is a contradiction, as L1 plus epsilon is strictly less than L2 minus epsilon. So let me check this claim for you, because it's not clear. Okay? So why is this the case, that L1 plus epsilon is strictly less than L2 minus epsilon? Well, this is an if and only if with L2 minus L1 being strictly larger than twice epsilon. Now remember the definition of epsilon. This is twice L2 minus L1 over 4. So this would be L2 minus L1 over 2. So, which is definitely strictly less than L2 minus L1. Okay? So, this is true, this is true. The fact that this is strictly less than that tells you that f of x is strictly less than f of x, which is a contradiction. No?
I mean, I got it wrong.
But now you've learned it, right? You see? It works. You've learned. So, and the proof is essentially the same as for the case of sequences. It's just that now a bunch of deltas are going to appear in place of a bunch of n-naughts. That's the only substantial difference. So, we may wonder if we are adding something. Do you have questions on this proof? So, we may wonder if we are adding something substantially different from what we did on sequences, and the answer is no. So, and this is proved by the next theorem. So the next theorem is going to show that computing a limit is the same thing than computing a limit along sequences. So L is equal to the limit as x goes to C of f of x if and only if for every sequence xn if C equal to the limit as n goes to infinity of xn, and you also want xn to be different from c for every n, then the limit as n goes to infinity of the sequence that is obtained by computing the values of f at the points xn, which I can do because I took them all different from c, is equal to f. So what I'm saying is that if I have a function and I want to check that its limit at c is equal to L, all I have to do is to pick an arbitrary sequence of points, xn, which is converging to c, okay? Compute the values of my function at these points xn, they will move around, depends on what is the sequence, and hope that f of xn, which is a new sequence of real numbers, has limit L in the sense of sequences. Okay? So, again, computing a limit in the sense of the epsilon and deltas is exactly the same thing as saying, pick any sequence that goes to C, compute f of xn, okay? So you see, what I'm telling you is that if the limit is L, then given any sequence that goes to C, with limit C, and taking value different from C, because I want to be able to compute f of xn, okay? So given any sequence that go to C without ever being C, I compute f of xn. And this sequence is going to L. Vice versa, if I do this test, I pick an arbitrary sequence, which goes to C never being C, I compute f of xn, and I check that the limit of this sequence is equal to L. If I can do that for every sequence, then it's like saying that this limit is equal to L in the sense of epsilon and deltas and the definition of limit of a function. Okay? So the two ways of looking at the problem are equivalent. So let me give you an example of how you can use that, this theorem that we're now going to prove, to show, for example, that a function has not a limit. Okay? So there is a very easy way, right? I mean, because if I can say that I want to compute the limit of a function at 0, well, it's enough for me to find two sequences converging at 0 such that my function evaluated along those sequences takes two different limits or doesn't update the limit. If I can do that, then I have found a contradiction to the theorem in case the limit exists. So for example, let me be more precise. Let's take, for example, the function f of x, so for example, as an application of this theorem. Take f of x equal to the sine of 1 over x, this defined for x different from 0. So my claim is that the limit as x goes to 0 of the sine of 1 over x does not exist. If you draw this thing with a computer, it will be very upset, and it will draw something like this. So very close to the origin, you will see you are packing more and more oscillations of the sine function. Because think about what this definition means, right? So 1 over x, when x is small, 1 over x is very large, right? And the function sine is just that. So the map that brings x into 1 over x is bringing the interval 0 delta to the interval 1 over delta plus infinity, right? Agree with that? So when I compute sine of 1 of x, in the interval 0 delta, I am taking everything that the sine does from 1 over delta on, which is infinitely oscillation, and I am packing them between 0 and delta. So it's like this thing that you see here is an infinite sequence of oscillations that has been crumpled into an interval of size delta, and then packed for you in here. That's the way to understand this function. Needless to say, since sine of n has no limit at plus infinity, right? You don't expect this guy to have a limit at 0. Now we're going to prove that. A simple way of doing that is the following. So let, say, xn be equal to, so let me think, I want 1 over pi over 2 plus n pi. Right. This is a sequence that goes to 0, right? Easy. So the limit as n goes to infinity of xn is definitely 0. Okay, then let me compute f of xn. Well, f of xn is the sine of 1 over xn, which means the sine of pi over 2 plus n pi. And this is just minus 1 to the power n, right? Because when n is odd, I got sine of pi, which is, sine of 3 pi over 2, which is minus 1. And when pi n is even, I got a 2 pi multiple of pi over 2 where the sine is equal to 1. Sine of pi over 2 is equal to 1. So this is definitely minus 1 to the n. And we already know this sequence has no limit, right? So which has no limit? So what is the moral of the story? The moral of the story is that so should L equal to the limit as x goes to 0 of sine of 1 over x exist, then by the theorem, which is written over there, it would be L equal to the limit as n goes to infinity of f of xn. But since I have found the sequence xn going to 0, okay, then it would be these for every, whenever the limit as n goes to infinity of xn is equal to 0 and xn is different from 0 for every n. And that's exactly what we have up there, right? So we have a sequence that goes to 0, never being 0, and if I compute f of xn, there is limit. Yep.
Can you explain in other words what you just wrote down? I'm not really sure, like in the bracket, I don't really understand.
Yeah, so if this function has a limit, then my theorem tells me that, you see, the theorem is telling you that if the limit exists equal to L, then on every sequence going to the limit point C, different from it, f computed there, which gives you a new sequence, as the limit L. So what happens if I take now xn equal to that? Goes to 0, never being 0, so it's admissible. I compute f of xn, this should go to L, if L is the limit of this function. But it cannot go to L, because it cannot have a limit. It's minus 1 to the n, so it has not a limit. This contradiction shows me that there cannot be a limit of the function at 0. Because, again, if the limit of this, if this quantity exists, if the limit of sine of 1 over x exists, okay, then this value, 5, 1, whatever you think it could be, would then be the limit of f of xn along every sequence going to 0. But here I've just picked for you a sequence going to 0, such that if I compute f of xn, I construct a new sequence which has no limit. So it cannot converge, okay? So that's a very simple but important application of this equivalence between the epsilon delta word and the theory with sequences, okay? Which is very helpful because it gives you a simple way of checking it something has not a limit. All right? Do you have other questions on this point?
What does that say right before limit?
Which has no limit. Minus 1 to the n. Here you mean?
To the right,
Here? Whenever.
whatever.
Oh, I'm sorry, yeah, this was really... Okay, so let me try to prove the theorem now, okay? So let us try to understand the two implications. Okay, so for example, let us prove the implication that if the limit exists, then limit as n goes to infinity of f of xn is equal to L for every xn such that the limit as n goes to infinity of xn is equal to 0 with xn different from 0 for every n. Okay. Let me try to prove that first.
Why did you pick 0 specifically?
Oh, you're right. Sorry, we have C, right? So, I mean, you could write the proof. I mean, at this level, a generic C or 0 is actually all the same, right? I mean, you can translate whatever you're working with. You can translate everything so that C goes to 0, and you study a new function, you compute the limit there, and well, no matter what. Think about it. Write down C. I mean, for what it matters, you could write the proof with C equals 0 and N equal to 1, if you like the numbers. So let's prove this. Let's prove that if the limit exists, then for every sequence, okay, so how would we argue? So first of all, pick a sequence. Pick a sequence xn such that the limit as n goes to infinity of xn is equal to C. Next, and pick your favorite value of epsilon. Positive. Okay? What we want to show, so we want to show the existence of a natural number such that f of xn minus L is less than epsilon whenever n is larger than n naught, right? Because I want to show that f of xn has limit L. The sequence f of xn has limit L. So I want to be epsilon close to L provided n is large enough. That's what I want. What do I have? So what I have is two things. So first, since L is by assumption the limit as x goes to C of f of x, since I have these, I know that there exists a delta positive such that f of x minus L is less than epsilon, provided you're never going to read these. Provided x minus c is positive and less than delta. Right? That's the definition of limit. Then I have property 2, right? Since c is the limit as n goes to infinity of xn, there exists a threshold and not such that xn minus c, xn is delta close to c for every n larger than a naught, right? since at the same time xn is different from c, right, for every n, we put everything together as follows. Okay, so you pick n larger than not. Take a second to write this down. So that's the situation, right? So we have that since L is the limit, there was this epsilon, we can find the delta such that we're epsilon closed at the point x, provided x minus c is positive, so x is different from c, and x minus c is less than delta. Okay? Then at the same time, since the sequential limit, the limit of xn is equal to c, then there exists some threshold and not, such that x of n minus c in absolute value is less than delta for every n larger than. Now we put everything together. So if n is larger than a naught, then I have xn minus c strictly between 0 and delta, right? The upper inequality comes from property 2, which was here, right? And the bottom inequality comes from this one, from the fact that xn by hypothesis is never equal to 0. All right? So xn is one of those points which belongs to the delta neighborhood of C, you see? So I can plug it in here, so I can plug x equal to xn in this condition and use this property. So this, if I plug x equal to xn into property 1, as I can do, right, because x equal to xn satisfies this condition, what do I get? I get f of xn minus L less than epsilon. And that's it, right? I proved exactly what I want. I pick an epsilon positive, and I have found a knot such that, provided n was larger than a knot, f of x was a distance at most epsilon from n. That's exactly what I've done, right? I've shown you that if x is larger than, if n is larger than a knot, then forget about what is in between. F of xn minus L is less than epsilon. Okay? So this is as wanted, and that's the end of the proof. For the implication, for this implication. Now we have to prove the other one, right? So we have to prove that if we have all the sequential limits, then we actually have a limit in the sense of the epsilon delta definition. So but we have to prove half of the theorem. The half of the theorem that tells you that if the limit exists, then you have the same limit along every sequence. And this is the one that we use to show that sine of 1 over x had no limit, right? Because we use the fact that if sine of 1 over x would have a limit, then sine of 1 over xn would have the same limit for every sequence xn, which we've shown is not possible. Because you can pick some xn so that sine of 1 over xn is minus 1 to the n. So, before coming to the other implication, we have questions on this one? Okay, so let's prove the other implication. So we want to prove that, so we know, now we know by assumption that if the limit is then goes to infinity of xn is equal to c, and xn is different from c for every n, then the limit as n goes to infinity of f of xn is equal to L. So what is wanted is that the limit as x goes to c of f of x is equal to L. And so the unfortunate thing is that there is no direct way of proving that, so you have to argue by contradiction. So essentially what we're going to show is that if the limit of your function is not equal to L, which could be that the limit is some other number or that the limit is does not exist. So we're going to show that if the limit of your function is not L, then we can find a sequence of points converging to C, all different from C, such that f of xn does not converge to L. Okay? So that's what we're going to do. Let me show you. So, and this is a good proof to see because the first step is really what does it mean that your limit is not L, which could imply that either the limit is a different number or that you don't have a limit. So we argue by contradiction. As follows. So we say, well, so say that the conclusion is false. So it is not true that limit that for every epsilon positive I can find the delta such that 0 less than x minus c less than delta implies f of x minus L less than epsilon. This would be my definition of limit, right? So the definition of limit would exactly mean that for every epsilon I can find the delta such that is if x minus c is less than delta, then f of x minus L is less than epsilon. So say that this is not true. What does it mean?
You cannot find such delta for every epsilon.
So, how do we formulate this precisely?
There exists an epsilon greater than 0 such that there does not exist a delta greater than 0 such that.
Exactly. So, more precisely even, so the fact that this is not true, so that is, saying that this is not true means that you can actually find some positive epsilon such that for every delta, so no matter what is the choice of delta you make, so it becomes a for every delta positive, there will be a point x within the delta neighborhood of C such that f of x minus L, instead of being less or equal than epsilon, is strictly larger than epsilon. All right? Do you agree with that? So the fact that if the limit is not L, it means that I can pick the value of epsilon, which would be my window around L, such that no matter how small is the opening I take around C, so no matter how small is delta, I will always find the point X within a distance delta from C, different from C, but within distance delta, such that f of x minus L is larger than my threshold. So my function will take a value outside this epsilon window around L whenever at this point X. So this means, so the fact that I have a limit means that no matter how small the opening here, I can find an opening there such that all the values of my function here are between here and there, right? Now the fact that the limit does not, it's not L, implies that, well, I can find an opening, L plus epsilon, L minus epsilon, such that no matter how close, so no matter how few points I consider, okay? So you see, for every delta positive means that no matter how big, small this delta here, when I look above my choice of delta, there will be some value, so there will be a point x in here, in this small neighborhood, such that f of x has jumped outside my box that I opened up there. Right? Well, because if not, it means that for a certain delta, right, all the values are trapped into this box, and then epsilon checks out for the definition of limit. So I have to pick another epsilon to find something that doesn't work. So it's like, no matter how close you go to C, you will always find points where f of x takes values outside this window, which is what it's written here. That's by definition what it means, that your limit is not L. So this could mean that your function has a different limit, which is not L, or that your function has no limit. Right? All the possibilities are open. I'm just telling you that the function has not as limit value that particular number L. And that's what it wants. Okay, so, but remember what we want to do, right? So I want to show that if this property holds, which is a property expressed in terms of sequences, right, then the limit must exist. So our assumption is expressed in terms of sequences. So far I have negated the deconclusion, and I've got this property. But I don't see sequences yet, right? I need some sequence to test my, to use my assumption, right? And how am I going to construct the sequence? I'm going to constructing using delta, because delta is arbitrary, right? So now I will pick a sequence of values of delta, and I will say, well, let this be C, and let's say this be delta 1, C minus delta 1, C plus delta 1. I can find the point x1 such that f of x1 minus L is larger than epsilon. All right? Then let me pick delta 2 smaller. I can find the point x2 such that f of x2 minus L is larger than epsilon. Okay. Let me pick now delta 3 even closer to C, right, than x2 was. By my property, I can apply it with every delta, right? So I apply it with delta 3. I find the point x3, which is even closer to C, such that this inequality holds. F of x3 minus L is larger than epsilon, and so on forever. So this way I will construct a sequence of points xn which are closer and closer to C. So a sequence of points that converges to C, such that f of xn minus L is larger than epsilon for every n. And this clearly prevents your sequence to be f of xn to have limit L, right? Because you're never epsilon close to L. Not even ultimately. So that cannot be there. So let me show you this in detail. So let us call this property, let me call it property delta, okay? Is the property that has been given a positive delta that I can find the point in this interval that violates the inequality. Yeah.
You just explained how that makes sense, but where's the contradiction?
Well, the contradiction is that by assumption, if I have a sequence that goes to C, then the sequence has to go to L. Now I'm going to construct for you a sequence which goes to C, such that f of xn minus L is always larger than this fixed epsilon. And so it cannot converge to L. So I'm telling you that if this doesn't hold, that doesn't hold. So which means that if this holds, this has to check. It's a usual contradiction argument. Okay, so let's see how we're going to exploit this property delta. So the fact that for every delta I can find the point. Let's see how we can use it to do this one. So let me set. So let me use the property delta with delta, say, equal to delta 1 positive and small enough to have C minus delta 1 C plus delta 1 contained in the interval of definition of my function f, right? Because I want to compute f at some point of this interval. So I want to be sure that my interval is contained in AB, where f is defined. Okay. So all I'm saying is that here I have A, here I have B, here I have C. I am picking delta 1 small enough to have C minus delta 1, comma C plus delta 1 contained into AB. Do you agree I can do that? If you want to be super formal, I can tell you that delta 1 will be 1/2, say, the minimum between B minus C and C minus A. If you like formulas, you can use that. Button, if you like formulas, okay? Good. So by using P delta with delta equal to delta 1, I discovered that there exists a point x1 such that 0 is less than x1 minus c, less than delta 1, and at the same time, f of x1 minus L is larger than epsilon. That's just my property E, right? For every delta positive, I can find a point at distance delta from C, so f of x is minus L is larger than epsilon. Apply this with delta 1. Okay, so far nothing bad. I mean, of course, it could be that there is a point x1 where f of x1 is a distance more than epsilon from L, right? I mean, this says nothing. It's just, this is a point such that. But now, what is the trick? Now I'm going to do this. I'm going to pick delta 2 even smaller, okay? So now let me use set. So let now delta 2 being equal to, actually, let me call delta n be equal to delta 1 over n for n greater or equal than 1. So for n equal 1, I got just the same definition as before. It's compatible. So delta 2 will be 1/2 of this delta 1. Delta 5 will be 1/5 of my original delta 1. So you can smaller and smaller windows around my point C. All right? Do you agree with that? Good. Okay. By property delta, with delta equal to this number delta n, I find so that there exists some point xn having two properties. So first, xn minus c will be less than delta n. And second, f of xn minus L will be larger than epsilon. Okay? Where, remember that this delta n is just my original delta 1 divided by n. So I got points xn closer and closer to C, but such that f of xn is always at this fixed distance epsilon from n. You never get closer than this epsilon. So you cannot converge. So what is the conclusion? Is that so the conclusion is that by 0, by actually directly by xn minus c less than delta 1 over n. So this tells you essentially that x minus delta 1 over n is less than xn, which is less than c plus delta 1 over n, right? And this tells you, so this is converging to c, and this is converging to c as n goes to infinity. This implies that c is the limit as n goes to infinity of xn, right? And you know that with xn different from c, for every n natural number, right? You know that because by construction, I also kept this property of each of these points is never equal to C. Okay, so I have a sequence which converges to C, right? And the points are different. So by my assumption, so now I am in the position of using my assumption, which is here. So thus, by our assumption, L must be the limit as n goes to infinity of f computed at these points xn, but this is impossible. It's impossible as by construction f of xn minus L was strictly larger than epsilon for every n natural number, where epsilon is the positive point, right? So if now I know that L is the limit of these guys, they are going to be ultimately epsilon close to L, no matter what is epsilon. But I already found an epsilon such that I am never epsilon close to it for every value of the sequence. So it's not that asking this ultimately will help me in any way. I just never takes values at distance less than epsilon from L. Okay, and this concludes the proof. So do we have questions here? Okay. So this last lemma is particularly useful to deduce from properties of sequences properties of limits, right? Because say that I want to check that the sum of the limits is the limit of the sum for a function as x goes to C. All I have to do is pick any sequence that goes to C and notice that the sum of the limit is the limit of the sum at the level of f of xn, of your functions computed on the sequences. Okay? And then I apply the theorem again in the reverse implication to say, but then the limit of the sum of the functions is the sum of the limits. So let me show you how this works. Okay? Since we have a few minutes, we can should take a moment. So okay, so let me try to explain what I mean by so. Let me write again the theorem that we have just proved. We have just proved that, say, little l is the limit as x goes to C of a function f of x if and only if little l is the limit as n goes to infinity of f of xn for every sequence xn such that C is the limit as n goes to infinity of xn with xn different from C for every n natural number, right? So that's what we have just proved. I've just changed the notation, but that's what we have just proved, right? That we have a limit in the sense of functions if and only if we have limits in the sense of sequences for every sequence that goes to C. It's the same thing. So now let me prove the following theorem. Let f of x and g of x be defined on AB and C be a point, of AB minus possibly the point C, and let L be the limit as x goes to C of f of x, and be the limit as x goes to C of g of x. So I have two functions which have limits. Okay? My conclusion is that then the limit as x goes to c of f of x plus g of x is equal to L plus m. And there is a very simple proof of that. So, proof. Pick any sequence xn such that the sequence converges to C, but it's never equal to C. Okay? So by, let me call this theorem 1, okay? And this is theorem 2, the one we have proved. So by theorem 1, the limit as n goes to infinity of little f computed at xn is equal to capital L, right? As well as the limit as n goes to infinity of g of xn is equal to m. Because my assumption is that L and m are the limits as x goes to c, right? In the sense of function. So in particular, if I pick a sequence that goes to C, I can use theorem 1 and deduce that along sequences I got the same limit. So I'm applying theorem 1 first with capital F, so with capital F equal to little f, and with capital F equal to little g, right? I'm applying it twice, separately to my two functions, and I got that. Okay, but this is what implies this. So this implies by what we have proved for sequences. So on sequences, we have proved that the limit of an plus bn is the limit as n goes to infinity of an plus the limit as n goes to infinity of bn, right? Remind that? So we have proved that on sequences. So this tells me that the limit as n goes to infinity of f of xn plus g of xn is equal to L plus m. Right? I just have to use the theorem for sequences. So for sequences, I have proved that the limit of the sum is the sum of the limits. I use that to check this. And now, I look at what I've said. I say that for every sequence xn that goes to C, if I take f of xn plus g of xn, I converge to L plus m. So I use again theorem 1, this time with capital F equal to f plus g, and I use the reverse implication. Right? So here I was using theorem 1, I was using the implication that goes from the left to the right. Now I'm using theorem 1, the opposite implication, with f equal to capital F plus f, to say that the limit as x goes to C of f of x plus g of x is equal to L plus m. Okay. Of course, you can actually prove this theorem directly from the epsilon delta definition of the okay? But that's just to show you that, for example, the limit of products of functions will be just the same proof. So f times g goes to L times m simply because we have already proved it for sequences, right? And concerning ratios, f over g, if g has a non-zero limit, then we can apply the theorem for sequences. An over bn goes to a over b, provided b is different from 0, to deduce that f over g goes to L over m, provided the limit is different from 0. So that's how it works. If you want homework,
Yes.
5-0.